Right, okay. We are coming to the last talk of this morning. It is a talk proposal, and is on the application of partial evaluation as a primitive for a modern network troubleshooting. So it's given by Anduo Wang from Temple University in the United States.
Oh, can we start? Do you hear me? Okay, cool. Great. So in this talk proposal, as a network researcher, I want to share with you folks my thoughts on how partial evaluation might be generalized to greatly advance network troubleshooting. The insight is this. We all know, and you folks know better than me, partial evaluation can be used to compile a program by specializing an interpreter. The enabling technique here is PE identifies and removes whatever information available at the compile time. This is a very general process, and the question we ask is, can we use this as a general device to pre-process complexity in modern networks that are ever growing in its size, semantics, and the concurrency and the failures it always had to deal with. Our initial progress is this. The PE formulation that we've seen previously in the previous slide that allowed PE to compile the program can be nicely adopted in networking. So here, the interpreter, instead of interpret a specific language, now provides the operational semantics of the network environment in general, given a certain concurrency and a failure model. And the target program is a network instance. We are interested in providing the specifics of this particular instance, such as the topology and the computation performed at each individual node. But the purpose in our formulation here is very different from the traditional PE that seeks to optimize the performance of a program. Here, we are interested in simplifying, generating a more tractable residual network that can be analyzed with legacy tool. By simplification, I mean to make the impact of concurrency and failure clear and explicit, to reduce the size of the network, and to remove certain semantics that might make troubleshooting hard. So that's the idea here, and if we can implement all of them, it's going to be very nice for networking already. But there's still a limitation, which is in the bottom you can see the root causes was given in the context of the residual network. It would be more interesting to provide that kind of feedback in terms of the original network, right? In terms of the original topology, event handler, decision logic, and also to provide feedback in the concrete concurrency or failure scenario. So to achieve this, the classic PE process seems to be inadequate, and we might need a generalization. We might need a reverse process, which we call PE reverse. So in the rest of this talk, I want to provide some evidence and also potential benefit how this can help networking, addressing all three sources of complexity, right? Size, semantics, and concurrency and failure. So let's begin with semantics related complexity first. We have the most developed idea here. So the complexity related semantics may be best illustrated in SDN, software-defined networking, which has been one of the biggest topics in the past 2 decades in networking that seeks to transition traditional distributed protocol into centralized software. And the 2 key motivations behind this is 1, to make innovation easier. Traditional distributed protocol was notoriously hard to evolve, right? The notorious ossified problem. And the second motive is to make things simpler because, again, right, networking, it has been notoriously hard to manage. It's very expensive, and so we want to make it simpler instead of making the admin operators master of complexities. And over the past 2 decades, right, not surprisingly, under this umbrella SDN, the techniques, enable technique is mostly language-based. So we've seen proliferation of new language DSLs coming up with new constructs, language support that make innovation possible. And indeed, SDN did a great job in fostering innovation, but it's hard to say whether SDN actually simplify networking or not, right? Many people may even argue that with SDN, networking these days are even harder to troubleshoot. And from a language perspective, it's not surprising because many of these new language features, they make innovation, but they also complicate debugging. So next, let me show you a concrete example based on our own research. Consider this requirement, a very simple requirement actually. So we would like to allow traffic from node 1, pass from 1 to 3, and reaching the destination 4. 1, 2, 3, 4. You can think of them as switches. The subtlety here is we want to make this happen. Only allow packets, right? Satisfying two asset control, both echo 1 and echo 2, under certain failures. We need to consider failures that might occur in the first link between 1, 2, and also link 2, 3. So a naive approach, right, to deal with this is we add backup links here in the dashed line here, and we consider all possible failure scenarios. We have 4 failure scenarios in this case, and we can enumerate, right, all of them. It's possible, but obviously tedious, right? So to avoid this kind of enumeration, we introduced Verilog, which is an extension of Daylog with conditions, right? I'm not going into the detail here, but the gist is with conditions, we are now able to encode the link conditions within the network itself, so that a single program here captures, represents the network behavior under all possible failure scenario, and verify one single Verilog program allows us to verify the network under all possible failure cases. So that's great, but surprisingly or not, the Verilog program is harder to understand or debug compared to standard Daylog, right? As illustrated in the 2 examples here, right? The top part is the correct configuration, and the bottom is a buggy configuration, right? It's actually not easy to see, even on this simple case, right? Why the placement of echo 2 in the second link 2, 3 might be a problem, because it's going to cause the bypassing of echo 2 only when the first link fails, or a seemingly irrelevant link. To help addressing these kind of like tricky debugging due to this new Verilog feature, we have some implementation showing how PE can help. And this is by a classic use of partial evaluation to remove layers of semantics, right? So given a Verilog program and an interpreter, PE can be used to remove the Verilog conditions. And here I'm showing some fragments of our implementation. The top right is the Verilog encoded in Prolog. We do the encoding in Prolog because that's our implementation language, and instead of dealing with Prolog, doing this embedding makes the rest of the implementation cleaner and simpler. And top left is the Verilog interpreter. You can see it's a natural extension of standard Prolog meta interpreter to incorporate the handling of the Verilog conditions. And the middle left is the partial evaluator. We implemented it. It's very primitive, right? We hand-coded the unfolding transformation. It's embarrassingly primitive, but it works. And the bottom left is the resulting residual program, and you can see how the residual program shows the features from both the interpreter and the Verilog program. And we then sent this residual program to debugger we also implemented, and top and bottom right is the debugging session, right? Showing you how we correctly identify the problematic configuration in terms of Prolog. Now, the remaining question is, identifying it in Prolog, that's nice, but can we directly identify the faulty line in Verilog? Can we actually develop a reverse process of partial evaluation? So in the review, we get very interesting feedback that reversing partial evaluation in general might be hard. What makes me optimistic about this in the context of troubleshooting is we are not dealing with a general reversing process, right? The important thing is it's more like mapping. It's more like establishing correspondence between the residual in the bottom and original for a long program we already know, right? So that's what makes us thinking it's not entirely impossible. Okay, so far I hope that it shows you how feasible, right, partial evaluation might help network troubleshooting, but we are still using some pretty standard, familiar application of PE. Next, let me show you some hopefully unfamiliar use of PE, considering the site-related complexity, which is probably best described in terms of internet routing, right? One of the largest computer networks we have so far. And BGP, Border Gateway Protocol, that's the single de facto protocol that's running the global internet, computing internet-wide path. You can think of that as the language spoken by every IP router to establish this internet-wide path. BGP research was really hot from 2000 to I think around 2010, and at that time, network researchers love to say, everyone loves to hate BGP because BGP is a broken protocol that generates numerous papers attempts to fix it. And one of the problems, it's still not fixed today, about BGP is it as a distributed path computation protocol, it doesn't provide convergence guarantee. It can diverge. It can non-terminating, do oscillating computation all the time. And the reason is because unlike some other standard algorithm like Dijkstra that use some universally accepted criteria to select a path, BGP allows the participants, like an internet service provider, to set arbitrary path preferences. Provider can favor a cheaper but longer path, right? That's causing this divergence problem. And determining convergence for a specific BGP instance turned out to be NP hardware, not surprisingly. And that makes the size of the internet really matters in this decision problem. And in the moment in networking, the way we address these scalability challenge is by reducing the network size before analysis and to compress the network size. Popular methods rely on heuristics that often exploit certain property of the network, such as symmetry in the topology. And in contrast, we think that partial evaluation might provide a far more general method to compress network. And the idea is if we have a BGP interpreter, essentially you can think of that specify the BGP protocol itself, and a BGP instance, its topology, and some partial information about the routing policy. By partial information in the top right here, you can see we mean all available paths, right, towards certain destination. For example, here you can see all the available paths towards destination 0. But we don't know the path preferences. We don't know how each node, right, each node preference among these candidates towards destination 0. And the opportunity here is we think that PE, by performing path computation in the BGP system that do not rely on path preferences, we have good reason to believe that PE should be able to identify nodes like X and Y that doesn't really depend on path preference because they only have a single path, right, to the destination. And by identifying them, right, we might be able to use PE to drop them, to eliminate them, and producing a residual smaller network, something like showing on bottom left here. So if we can get that, and suppose we also get supply additional path preference information, then we can leverage traditional technique, right, to actually analyze and identify the problem, the so-called unsatisfiable core, and minimal set of routers that actually causing the oscillation. Right? In this case, the intuition is regarding destination 0, node 1 and 2, they are preferring each other to get to the destination. Right? So there is some cyclic preference here that's causing the divergence. Okay, if we can do all of this, that's nice. It's going to be a very general technique, right, to address, identify, detecting oscillation. But still, right, the recurring challenge here is, can we map the identified minimal call, right, in the residual network back to the original BGP instance, right? How to do that? Okay. And finally, let me show you the last scenario we identified. Hopefully, maybe the most unfamiliar case, right? And also the least developed idea here, using PE to address complexity related to concurrency and failure. So concurrency and failure, right? It has been a problem for networking since its birth, right? But in the emergent paradigm called INC, in network computation, the problem is severe because traditionally we have well understood techniques to address those distributed system complexity, message loss, reordering, etc. Right? We have this standard technique, timer retransmission. The problem with these techniques is they are expensive, and that's why these techniques are only employed in the end host, right, in TCP for them, not in the switches or routers with limited resources. But with INC, we are designing protocols for switches and routers, and so these expensive techniques are not abandoned, but they are avoided. And we are seeing a wave of new lightweight protocol that the designers, these INC designers, they claim and believe the protocol correct, but it turns out to contain bugs. So we asked, can we use PE to facilitate, right, the INC design? The idea is to use an interpreter to model the concurrency and the failures the INC design is considering, and use PE to mix the concurrency failure model with an INC event handler to generate a holistic model that can be analyzed using, say, an existing model checker. And again, the result is to how to map it back to the origin to explain the problem in terms of what part of the event handler is causing problem in what concurrency and the failure scenario. So that's my talk, and I hope that I show you the potential feasibility and also challenges with generalizing partial relation to advance modern network troubleshooting. Yeah, so thank you. Ready to the
Thanks, Anduo. It's interesting to see PE be used in a different context. Any question or feedback for the speaker before heading out for lunch?
Thank you. Very, very interesting. So, in a scenario that people probably might consider more realistic than ever, you might have a router or a switch provider, okay, who will put in a mode where it is intentionally actually creating divergence, right? So helping create divergence in order maybe to take down the internet at some point. So is that, will your analyses in principle help? You probably have to know something about the internals of the individual switches, I guess. But will your analysis then maybe at scale help at identifying possible subnetworks or paths, routes that might be involved in a divergence attack?
In divergence attack.
Yeah, think of it as somebody not being interested in convergence, but actually in a divergence.
Okay.
There's lots of people are probably going to be interested in that.
I'm not sure.
Not us here, I guess.
Okay. Okay, let me try to rephrase your question. So I think there's a few issues involved here, right? One is what's needed for us to analyze the divergence, or whether we need access to the software, to the program. And that's actually an excellent question. So in general, here we assume we have access to the internals, but it's not always the case in network in general. But on the other hand, right, reverse engineering, that's lots of effort in networking, right? There's many techniques that do not rely on the internals. It can be a big research in itself, but in this early stage, we assume we do have access to the internals. Now, on the other hand, regarding divergence, if it's a networking problem, I'm not sure whether you really need to investigate in the router or switches to cause divergence. There's many other ways to cause divergence, right? So you talk about, I'm not sure if I understand your question clearly. So when you say calling divergence, the potential Can you elaborate on that?
Just somebody attacking basically the internet at scale by providing, providing cheap switches or whatever that work normally or mostly until they're intended not to work anymore.
Can you elaborate on
work in
potential?
The sense of actually making it, diverge in this case.
In divergent. So there indeed, right, there are real incidents in history reported, and all of them was caused by misconfiguration, not intention, not malicious intention, by misconfiguration. And it bring down the internet for minutes and hours and minutes. That's big revenue loss.
Okay, let's thank the speaker again, and it's time for lunch.